Okay, so again, thanks a lot, everyone, for joining. This is the final in the series, in a way. This is like the last module in Awakening, which is controlling your source, so all around basically controls. So again, we've got people on that are following the course through, and hopefully this is going to help you through that if you are on that module. We've also got quite a lot of people. I've been looking at the data of the people that are on, of where you're at in your journey, and to be fair, I think more people have actually completed the course that are joining these calls, which is also really nice to see. And that's what I wanted to get from all of these. So, this was just an idea of let's just start doing it and see what happens. The idea was to bring people in that have finished it, or hopefully get them people in, and people obviously that are on the course, and then hopefully try and get this peer-to-peer stuff going again. And it's been amazing to actually see it coming into action. And as I say, we've got like the guys from the Netherlands joining as well, which again, a little bit crazy to think about. Thanks for joining, everyone. So yeah, it's again, whatever happens after this, I just wanted to say thanks to everyone for joining every week. It has been great to speak to everyone and see what's happening here. And again, these recordings that are going onto Facebook and maybe onto YouTube or wherever it's going to end up, I think it's going to help a lot of people. Not just on the course, people that are just starting out in this industry and seeing what they should be learning, all that kind of stuff. So yeah, I just want to say thanks for everyone. And moving on, if you've got any suggestions of what we do with these kind of things moving forward, just drop me an email anytime. If you've got any ideas for sessions or anything like that, I'd love to hear it. We could just go through and do the mastery sessions. I know I've already done mastery sessions with people, but I didn't record them. We could go into a lot more detail and stuff like that. So yeah, always open for ideas. Just again, I put this on every week. I know, I've watched a couple of sessions back, and I sort of bored myself just listening to myself moan about the industry and the training in the industry. So, I think we've got too many people in the industry doing that kind of stuff without actually doing anything. So I'm not going to, start all that kind of stuff. Just a bit of background. I was an installer. I was an engineer. I was a gas engineer for 10 years. Moved to Australia. I got into heat pumps. Came back, found training basically, and then I was a lecturer for a few years, and I worked in different manufacturers as training managers, all that kind of stuff. So again, I've been there. I've been the gas engineer. I've made the transition into heat pumps, and hopefully, I can pass that knowledge on. Similar to what everyone else is sort of doing at the minute. So yeah, a bit of background about myself, not boring you. The agenda's been on every week again. Again, for the people that haven't been involved, it's not death by PowerPoint, hopefully. I do want to start the discussions. I want people to get involved. I want you to share your knowledge, answer the questions as well. This module in particular, the way I put it together, it's sort of, I don't want to say it's extremes, but it starts very basic and then we end up somewhere completely different. So what I'm sort of emphasizing at this point now is I don't want to sound like I'm condescending anyone. If I'm asking like a really simple question about weather compensation, or simple in your mind, could you please answer it as well? Because, somebody on this call or somebody watching this recording might not understand that. So, it'd be nice for people to, even like the really simple stuff, if you could just, like you have been all the way through, to be fair, even if you fully understand it, if you could put your spin on it, answer the question, that'd be great. I'd really encourage that, because, that's what we've been doing all the way through, and it's been great. There's a hand button down at the bottom. If you do want to speak at any point, just press that, and then I'll stop talking. Don't wait till the end to ask questions. That's not what this is about. This is discussion. This is peer to peer, all that kind of stuff. And then the bottom, the aim is to understand, not just to pass the test. Again, as I put this together, this is what was in the back of my mind the whole time. It's not about, here's how you answer question 1, here's how you answer question 2. That's not what it's about. It's understanding the concept. So then you can answer question 1, question 2, but you actually understand why you're answering it. And I hope that's come across. And again, with this module, I've gone even a step further, and like, how do we put this into real life, like actual on the controls that we're going to use every single day? Because I think that's a big thing that's missing in the training industry. Again, starting calling the training industry again. That's a big thing, like how do we actually apply it in real life? And this is what I've really focused on this module in particular. But again, for the people that are still on this module on the course, it will help you out. But I hope it helps you. Hope it helps you anyway. So again, module 7, last one in Awakening. And just for last week, again, if you've not seen the recording, if you weren't on the session, module 6 was emitter sizing. Again, we went into loads of detail on this, and it was really great interaction for everyone. We went above and beyond the Awakening. I'll be completely honest. If you've looked at it since, like a lot of that was actually on the mastery emitter sizing, but I just wanted to see where we could end up. So yeah, and we talked about what apps we would use. So the High Tools app is a great app. obviously looked at the Heat Geek app. So, if you worked under Heat Geek's umbrella, that's what you'd have access to, and obviously how it helps you in the real world. And then, yeah, as I say, the key message from the end, and I hope I've had some nice feedback on that. And I think that hopefully it's hit a few people of like just being able to choose, let's say your lowest flow temperature based on your emitter size. That's not what you have to design into in every property. Have that conversation with the customer, like, do they want every single radiator changing so you can get the flow temperature down to 40 degrees, or can they not afford that? Can you go to a higher flow temperature and a lower installation cost? And as long as you've still designed it, that's still perfectly fine as well. So the key message is, just because you can design to the highest scope, again, always have that conversation with the customer and find out where their happy medium is. They might want that. They might want to be on the leaderboard, which is great for them people. But some customers might just want a cheaper installation. And as long as you've designed it correctly, that's perfectly fine as well. So again, use that knowledge, but that knowledge doesn't mean that you have to design to maximum. You could design to anywhere in between. As again, you're still using that knowledge that you've learned. So yeah, it was nice to see people, get that concept as well, which is always great to see. Okay. So starting now with the module 7 stuff. If you've been on these in the past, you might have seen a variation of this question. I think I might put it in the heat loss one. But basically, I'm sort of trying to bring the module together, because that's what this module all boils down to. Like, we've learned loads of different concepts, and then when you put them all together, that's when it's like, okay, so how do you actually control all these concepts that you've done? So this question here of like, what would the heat loss be in kilowatts when it's 12 degrees external and 21 internal? Okay, so you've got your yellow box there, which is second row up on the right if you can't see. So second row up on from the bottom, sorry. Anyone want to jump in about how you would work that out, and also the answer, if you don't mind? If you've got a calculator with you, you might need it, using your phone. So what would the heat loss be for when it's 12 degrees external in this case? And if you, go on, Steve.
So if you've got your 10.8 kilowatts, turn that into watts, 1080 watts, divide that by your temperature difference at 24 there for the top one, that'll give you a heat transfer coefficient. And if you times that by 15, should give you the kilowatts at 12 degrees outside.
Okay, where's your 15 come from there, Stevie? Sorry, mate.
So -3 plus the 12.
Okay. With that one, mate, you were spot on. You were absolutely spot on all the way through. Anyone want to jump in? And so Stevie's completely right. Without me telling everyone the answer, the first thing you would do is find your heat transfer coefficient, so your HTC, which again, as Stevie mentioned, is your total heat, or any of them heat loss. You can choose any of them. So he chose the 10.8. Divide that by the temperature difference, and that's telling you then what HTC is, which is basically how much does every 1 degree equate for in terms of watts or heat loss or heat gain, whether you're going up or down. So you've got that HTC now, that number. Then to find when it's external of 12, what are you multiplying that number by now in this case? Anyone jump in? Colin, I think you were first in there, mate. You're on mute.
Yeah,
9?
Yeah.
Yep, nice, brilliant. So yeah, exactly right. And again, like you times it by 9 because that's now your temperature difference for 12. Stevie, you see where that comes from, mate? Yeah. You know what? As soon as you started saying it, I was like, have I wrote this wrong? Because you have never got any of these not right. And I was like, oh shit, I've put it in wrong. But no, yeah, it's just a slight mistake there, mate. But yeah, spot on. So again, as Stevie mentioned, that's how you work it out. That's that step by step. That's what we need to understand of like, what are we actually doing here? So again, the key point from this, take any of them heat losses that I've already give you. So like 10.8, 7.2, whatever. Then you divide that by your temperature difference. So, if you took the 10.8 one, your temperature difference was 24, and that's between -3 and 21. So then 10.8 divided by 24 gives you 450 watts. So every 1 degree, as it says there, is 450 watts. So again, like all you've got to do then is that every 1 degree is 450 watts. How many degrees difference have I got? Well, I've got 9 in this case with the 12 degrees outside and 21 inside. 450 times 9 gives me my 4.05 kilowatts. So again, you're using that triangle. If you see the triangle on the left-hand side there, this is all in module 2. So the heat loss calculation, I think it's in module 2. it's vitally important. This is this is the basis for everything. This is like how heat comes in and out of a property, basically. This is deeper than heat loss. This is like the fundamentals of everything. So again, understanding that triangle or understanding what this is so important for everything else. And, you know, to move away from the maths, because again, it's so easy to get stuck in the maths when you're doing all this kind of stuff and you're like, oh, well done, I've worked out the question. Like when you step back and you look at it, that the message here is that heat loss is completely dependent on so many different factors. And in this case, it's dependent on outside temperature. That's the thing that I've changed in here. So again, you know, when you say, oh, my heat loss in my property is 10.8, it's like, yeah, but what is it today? And it's like, oh, well, today it's 12 degrees outside, so it's 4.05. Or today it's 21 degrees outside, so it's 0. It's like heat loss is on a scale, like, you know, or heat gain is on a scale as well. It's never just this. And when we start thinking about this, like as a scale, then the need for weather compensation is like, well, obviously, like, why would you not do that? You know, but again, it's just understanding this table is just so important for the rest of everything else that we're going to learn and what we're going to implement. So again, heat loss is obviously changeable. This could be one whole day. So you could potentially fit, you know, let's say you fit in a 12 kilowatt unit for this example, because you design to -3. When it's 15 degrees outside, you might still want to heat the house. Can your 12 kilowatt unit modulate all the way down to 2.7? Like some units possibly can't. So then what happens then? How do you limit cycling? And again, this just isn't just this question. This is like, oh, okay, so what happens if I do this and what happens to do this? How does volume come into it? And again, like, there's a lot of things you can think about just from this table. So yeah, nice introduction. So just on that, again, I've tried to limit the amount of stuff on this screen, hence why I'm hiding the bottom half of for the minute. So I put like this as progress with a question mark. Again, like we've got a thermostat or a programmer on the left-hand side. You know, obviously I'm not going to state the name of that, but I think everyone can work out what that is, like a cartoon version of that. And basically this is like what I'd probably say the majority of homes using a gas boiler system at the minute are installed like. So, you know, you have this thermostat programmer on the wall, and then basically what you'd have then is like, typically you'd have 2 zone valves. And again, like, you know, if you don't know what that is, there's just basically a spring inside of that. It gets power and it opens, and then when it loses power, it closes. So it's basically opening and closing, doesn't do anything else, doesn't sit halfway or anything like that. And then what happens with that is when it's fully open, it sends power to the boiler and the pump and says, come on. So then when it's closed, obviously then it tells the pump and the boiler to turn off. And again, like what this is basically showing is how we've always typically in some form controlled our heating ever since like the 1960s or whenever, you know, people first started to get central heating on a larger scale. So, you know, if we just step back and look at what happens here, like you've got switches just all the way along. So, you know, it's proper simple, old school that we invented, you know, 100 years ago. If this switch does this, then it sends power to this next stage. Okay, make the switch and I send power to this stage. It's as simple as you can possibly get. The only thing that's smart about it at the start is that you can do it off your phone now, but it's still doing the exact same thing. It's just sending a message across. So, you know, if we start at the very start there, you know, you set your programmer. So you said between 6 and 9 in the morning, I want it to be 20 degrees. So your programmer looks at that, or your thermostat part of your programmer looks at that and says, okay, so the target is 20 degrees. It's currently 18 degrees. In this case, I need to come on. So then it sends power, 230 volts in this case, across to the central heating zone valve in this S-plan system. And then what that valve does, as I say, it's stupid, it's silly in a way, it just opens or closes. So as soon as it gets power down that brown wire, it opens the valve up. And when that valve's fully opened, it basically, inside there's a switch, and it hits the switch, which is the orange wire. And that orange wire then keeps that voltage coming and then basically sends it to the boiler and sends it to the pump, normally on a switch live, and then that says fire up. Where it doesn't tell it is what temperature to fire up at. Okay, and then again, if you were to follow it through on the hot water side, it's exactly the same. It just goes to a cylinder thermostat there. I wanted to show that one in particular because that's a more modern style of a thermostat. But again, it's still, you know, on off. It's still not modern in any way. Just opening the hot water zone valve now. Key thing here, the orange wires join together. So again, you know, if you're going out to this job and you just had one demand on and you weren't looking at what you turned on, if you put your multimeter in and said, okay, there's 230 volts on orange, you'd actually have no idea what the demand is. You just see, because obviously they're joined together. And if you think about that key point there of these orange wires joined together, that boiler and that pump do not understand what the demand is. So again, they don't know that you've only asked for heating and you only want it to raise from 18 to 20 degrees. That could be thinking you need to heat a full tank of water, you know, like 300 litres of water up from 10 to 60 degrees. So again, it's a stupid way of doing it because it's got no control in a way. And what it's doing is actually it's reacting to what you're telling it. So, you know, what's going to happen is that boiler is going to fire up and it's going to throw its kilowatts at that system. And it's going to say, oh, actually, I'm a 30 kilowatt boiler. I've just thrown 30 kilowatts at this house, but the heat loss today is only two kilowatts. Suddenly that return temperature from that heating is going to come back to that boiler and say, I'm red hot. And it's going to go, okay, I should probably turn down. And it starts to modulate down. But again, it's reacting. It's not actually thinking about what it's doing. It's like, have all this heat. And it's like, oh, actually, turn down. And have all this heat. And it's like, oh, turn down. You know, and it's again, it's not a clever way of doing it. And what you'll also find, obviously, is once that target temperature is reached, so that 18 becomes 20, suddenly that power is split there and it's just cut off at that first step. So obviously everything else just turns off at that stage then until obviously the temperature drops down and you know it comes back on. So it's on-off controls, and that's the key thing here is it's just on-off. All these things are an on-off control. And on the right-hand side, at the very far right, we've got a TRV there. So, you know, thermostatic radiator valve, they were invented because we knew we was going to put too much heat into the system. So we needed something to say, stop that room getting to 30 degrees or stop that room getting too hot. So again, that's why, you know, we invented them. And when you look back at that slide and it's like, yeah, but heat loss is changing all the time. So why would you do that? You know, and again, it's just a hangover in a way from the old way of doing it. And this was the old way of doing it, you know, so instead of having a programmer stat in one, you had a programmer, then you had a thermostat. So, you know, you press the heating button on the programmer, it sent 230 volts to the thermostat, then the thermostat sent power to the zone valve, and then it did the exact same thing. Like, you could look at that top system going, oh, that's a modern system. That it's only modern compared to the bottom system, which was like 1960s, 1970s, 1980s. Like, it's still not a modern way of doing it. You're still putting too much heat into the property, then reacting and saying, oh, turn off. And obviously for a gas boiler, that's bad, but it's even worse for a heat pump as well, because obviously cycling on a heat pump is obviously terrible for efficiency and, you know, the longevity of the parts and things like that. So again, if I'm teaching people to suck eggs there, I'm really sorry, but I think you just hopefully can grasp that a lot of people don't understand this in a way, and like it's new to people, and you know, that's fair enough, because as I say, you know, when I was teaching in colleges, I was teaching people how to wire these systems up, and that was the people are literally leaving colleges. Oh, this is what we do. And it's like, well, no, this is not what we should be doing. Like, yes, have an understanding of it so you can fix these systems and you can change them, but this is not what we should be doing as a first priority. We should be doing priority hot water. So yeah, hopefully that makes sense. Again, any point, anyone, just stick your hand up if you're not sure what I'm talking about. Okay, so compensation controls, that's what we should be promoting, obviously, on any system. So, you know, modern gas boilers, as I talked about on module 3, I think, you know, work more efficiently when they're condensing. They're only condensing when they're under like 54 degrees for the return temperature. And again, if you go even lower, you can get the whole heat exchanger condensing, all that kind of stuff that we talked about. So again, we want everything to be running at as low a flow temperature as we can to maximize efficiency. And you know, with the way compensation controls work, and again, it is teaching some people to suck eggs, but, you know, let's just start here. Like the maximum temperature, the maximum flow temperature is basically when it's colder outside. And then it needs a minimum temperature when it's warmer outside, because all it's doing is looking at that table that I shown previously and going, okay, so you need 10 kilowatts today because it's -3 outside, or you need 2 kilowatts today because it's 15 degrees outside, you know, and it's basically that curve is just following how the heat loss is going. And that's how compensation controls work. Like, they don't just do the on-off kind of stuff. They're actually proactive. They're actually saying, this is how much heat you need at this one point in time. I'm not going to give you too much. I'm not going to give you too little. I'm just going to give you enough. And what you'll get from customers, if you've ever started to install this, is suddenly customers are like, I feel really comfortable now. Like, this is a more comfortable way of living. And they always say this with heat pumps. It's like, it's a more comfortable way of heating the house. That's not the heat pump. That's the compensation controls they're referring to. So again, start doing it on your gas boiler installs as well, and they'll get this same effect. So yeah, moving into putting that into sort of real life in a way. This is, but you might have seen this from the training anyway. So this is obviously shown in the training quite a lot. This is how we set them compensation curves, basically, of how much heat we put into that property. And again, because obviously every property is different, you have to set this for the customer. So if you can see down the left-hand side, on the y-axis, you've got flow temperature there in degrees Celsius. Down the x-axis at the bottom, you've got outside temperature in degrees Celsius. And then up the right-hand side and across the top, you've got your slopes or your curves, basically, of which curve would you select. And, you know, like, again, this is, at this moment in time, this is set for a 20-degree room temperature. So you could say that, you know, well, you do your design, and obviously, and then you're saying, I'm going to design to, let's say, -5. And once you've done your design, you work out, I need, you know, such and such flow temperature at -5. Basically, what you do is you go up from -5, you go across the flow temperature you've chosen, and where they meet, then that's the curve, basically, that's saying that that's going to follow that suit. So again, hopefully that makes sense. If you don't understand that, please shout up, because if you're still on Awakening on this module, every single question is relating to this in essence. So again, like, so vital to actually get where this is coming from. I'm gonna throw this question out, and again, you need to fully grasp what we're asking in this question and fully understand what the chart is showing you here as well. So this question here, like, you need a mean water to air temperature delta T. So again, we're going back to what we did last week in a way. You need a mean water to air temperature delta T of 22.5 when it's -3 outside and 20 degrees inside. You're designing a system with a heat pump on. So you're going to run it at a delta T of 5 in this case, across the flow and the return. Which curve would you select? And I know, like, from doing these kind of things in the past, it's probably hard to see exactly on this chart if you're looking at it on your phone or whatever you're on. But what I'm sort of trying to grasp here is, how do we get to that stage? Like, could anyone talk me through step by step to answer this question? Which, again, like this, if you can answer this question, you can answer every single question in this module if you're still on that. Anyone want to jump in and say, how do we even start here? And again, use the knowledge that you've learned from the other modules and just sort of apply it all in one go now. And again, welcome anyone to have a crack at this. Where do we start? Is it Walter, is it, sorry?
Yes, yeah, you pronounced that correctly.
Nice.
So the room temperature is 20 degrees. We have a difference of 22.5. So the water temperature should be, the mean water temperature should be 42.5. So the flow temperature is 45. Then we have -3. So we look at 45 at -3. Will give us about slope of 1.0.
Awesome, absolutely perfect. Well, so that's the example of, like, the perfect example of how to answer that question. I love it. Brilliant. So the first thing you said was find the water temperature, the mean water temperature. So again, in the question, we've already given you the mean water to air temperature delta T. So that's basically the difference between mean water temperature, obviously, and an air temperature. So what is the difference between that? Because, as you say, we know the air temperature is 20. We can find the mean water temperature difference now. So basically all we've got to do is take the 20 and add on our mean water temperature to air temperature delta T, which is 22.5, add that on, and then we come up with 42.5, as you rightly said. But again, that is mean water temperature. And when I've seen this in the past, and when people put the questions onto Facebook, if they're stuck on this, they keep getting it wrong. The reason they get this wrong, and I've seen this so many times, is that this chart is focusing on flow temperature. It's not related to mean water temperature. So don't stop at 42.5. You need to find flow temperature, as you rightly said. And then to find flow temperature, you need to look at what delta T we're running this at. So in this case, we're running it at 5 degree delta T. You know, if it was a condenser boiler, it might be going 15 or 20 degree delta T. So again, to add on that delta T to find your flow temperature, you just half it. So half of 5 is 2.5. Add that onto your mean water temperature, and then that will give you a flow temperature of 45. So you've got a flow temperature of 45, you've got a return of 40. So your mean water temperature there is 42.5. And then obviously the next stage then is when we find the -3 on the chart. Andrew, you raised your hand there. You want to jump in? And you're on mute if you're talking. Sorry. It's the far left microphone button.
Yeah, I've got it. I'm getting there with the technology.
Yeah, no, I like it.
A while ago, I was doing a job for a guy who was a commercial controls engineer. Wow. And he kept talking to me about weather compensation ratios. And I couldn't quite work out what he was talking about. And then he explained to me that the ratio, if you look at the numbers, they actually form a ratio. So the original weather comp curves were a straight line. They didn't follow the curve to suit the adaptation of the radiator outputs or the lower adaptation of the underfloor heating layouts. They were a straight line and they were a ratio. So if you worked out basically your original delta T between your design outside temperature back to your room temp, to your internal temperature, so you'd end up with a gradient, say of 24 in your previous example. You would then divide the difference between the 20-degree flow and your final flow temperature by that gradient. And the ratio of those two numbers would give you the ratio for your curve. So you could actually determine the curve value for most appliances from that. Now, it's not quite right because Vaillant curves don't match Viessmann curves, but they follow roughly the same principle. So without knowing much at all, you can go straight to your control, pre-program the curve based on that ratio, and then you can just make your final adjustments later. So that's quite a useful thing to understand. There was something else I was going to say, but I've forgotten what it was. But, anyway, I hope that's useful.
It's definitely useful. Yeah, I really appreciate that, Andrew. Anything else like that, please jump in. And not to sound like a fanboy.
I remember the other one in a minute, but
I think you've done a video on that in the past, haven't you, to explain this on YouTube, if I remember.
Yeah, but
right.
I do the videos when I wake up at 3 in the morning. I'll produce a video and then I won't remember it the next day.
Fair enough. Yeah. Yeah, so there's a video from Andrew doing that on YouTube to explain that again. And again, it is a good point. Not all manufacturers use the same, but again, they're roughly in the right area as well. So yeah, it's a nice point to raise. So yeah, so we found our flow temperature here. And then again, this is just teaching you how to use the curves, which is, it's simple for some people, but again, this is a new thing for quite a lot of people moving from the gas industry, used to fitting, the programmable stacks or, whatever, the S-plan systems. So again, just stick with us. Again, like we're finding -3, as Walter said. So again, it's around about there. And then that's our -3. And again, we know our flow temperature now needs to be 45 degrees in this instance. So we're going to draw a line at 45 degrees. And then where they intersect there, we're coming up at around 1, as he rightly said. Somehow you're seeing that on the screen, which is really impressive because I can't even see it on my 2 screens. So yeah, that's how we would find what curve we would set. Okay, and hopefully that makes sense. And again, if it doesn't, please either drop me a message or stop me during this, and we can go over it again. But the key thing here, it's flow temperature. It's not mean water temperature. So you need to find flow temperature. This is what all this is based on. Once you've got flow temperature, find your outside design temperature, and then go across. And a nice thing to show people if they don't fully understand why this is important, that's when it's -3. It's 45. If you followed that number 1 curve down now to 0, it would show you that now it's asking for like a 42-degree flow temperature. Or if you go down to 5, it's showing you that you now need a 38-degree flow temperature. It's just that same thing of the table, just in reverse. It's colder, so I need higher temperature, or it's warmer, so I need lower temperature. And that's what that is signifying there. So again, really important to understand. One thing that we probably don't talk too much about is the bit that's coming diagonally where it's set room temperature. Again, if your customer isn't setting theirs to 20, if they've set it to 25, all that happens there is every one of them curves then just shifts up a bit. So, instead of starting down at 20, it would start at 25. So again, the curve just shifts up a little bit, and it's just called a parallel shift in that case. So, if the customer's turning their stat up and down, that's all they're doing basically is just adjusting where them curves sit. Obviously, we're going to go into more detail for real life purposes as we move forward. But again, just a little bit of information about what's actually happening. So now, again, going beyond the course, because this is what we need to be doing. It's not like this is the gospel. Let's see how we apply it in real life. So you'd set that curve at 1, as we've worked out. What about in real life? What would you set the curve to? No one wants to say. Colin, what would you do?
I should start with 0.8.
Nice. Why would you do that?
Just to see, maybe you can win a little bit more efficiency on the system.
Love it, mate. Awesome. That's what we do. Okay. Heat loss calculations, unfortunately to say, as I've said on the heat loss one, are never 100%. You're probably wrong, unfortunately, as good as your job that you are, and as well trained you are, you can't account for everything. So that it might be slightly out. There might be more internal gains in some properties. There might be like loads of different factors that could influence this. So the Heat Geek advice, and again, you can use this on your own jobs as well, obviously, and please try it, is even though you've calculated it to be 1 in this case, in real life, start lower, start at least 1 step lower. And then what we want you to do then is keep going lower, because you'll never find out where you should be unless you get to that point where it's like, I'm cold. It's like, oh yeah, sorry about that. I'm glad. Let's move you up a little bit, and that's where you are. And again, I've mentioned this a few times, but this is what you need to do, as Colin said, to extract that absolute maximum of that efficiency. Every degree counts in a heat pump. In any installation, every single degree is so important. So let's keep getting it down as far as we can. So, like, just to emphasize this and, show what we want to be doing in real life, that for people that are on the upgrades platform, which is like Heat Geek's umbrella, I don't know if you're aware of this, but I've put it into some WhatsApp groups that we've now got a simulator for the Vaillant sensoCOMFORT, which is the Vaillant controller where you can set loads of different stuff, really. And I just sort of wanted to show that for people and start talking about controls in real life and what you would do in real life. So, first thing is, this is for people that are on the upgrades platform. So, if you do want to know where it is, it's in my resources, and you can click on that. The key advantage of using this, I'll just start it while I'm talking. The key advantage of using this, if you've never seen Vaillant controls before, you can have a play about before you get into someone's house, so you can actually work out how you would set this on your commissioning. So the first thing you do is obviously choose what appliance you've got. So in this case, I've chosen the heat pump, the Aerotherm there. You can choose how many heating circuits you've got. So in this case, it's 1. And then again, this is exactly how the controller actually works in real life. So, you can have a play about, you can go into the settings, you can change anything that you want to learn about. And I'd really encourage people, before you do your first install, to do something like this. So, as I'm going through there, you want to go, this is to change the curve, you want to go to installer level. On the sensoCOMFORT, it's 00, unless someone's changed the code. And then again, like, you want to go to installation configuration. This is how you would find, obviously all this is in the manufacturer instructions, but we all know that no one reads them. And then, you want to be going down here now to basically circuit 1, as it will show you, hopefully. And as you can see, everything's changing in real time, as it would be, in the real world. Obviously, just doing it with your mouse. You can do it on your iPad and stuff as well. And then there's your heat curve. So again, it won't show you the curve in this case. So you need that reference material of what does this curve equate to. But again, you can always set that depending on, what you've calculated or what you assume. So as I say, don't always set it to what you've calculated, go lower. And then obviously that's how you would set that. There's loads of other stuff here that we are going to talk about some of these things as we move forward, but there's loads of stuff to play about with there. So yeah, a couple of hands went up there, I think. So Stevie, do you want to jump in, mate?
Yeah, just while you were on that one, see, I had a wee shot of the simulator just last night, and I was wondering, see, I'm not sure if you can bring it back up or not, but it's got zone 1 and it's got circuit 1. What's the difference between the circuit and the zone and on that controller?
So with that one, so it'd be like, basically, if you had a zone that was running at a different temperature, so you'd have like a electrical mixer inside of it or something like that.
Yeah.
Yeah. So that would be your zone, basically.
Yeah, but obviously you could put the different zones in, but is that why they worded it like a circuit, and one's for a circuit and one's for a zone?
It's a good question. Does anyone know that? Why they worded it that way? I'll take it away, mate. I'll ask for you.
No worries. No worries.
Good question. Andrew, did you raise your hand as well, or is that a previous one?
No, oh, is my hand raised?
It was. Don't worry.
Okay. No. So I missed the question actually just then. So I'm trying to work on site at the same time.
No, so the question was, what the difference between circuit and zones on the Vaillant sensoCOMFORT? What's the reason for the difference in wording? Do you know that?
I don't know. No, they've got some very strange concepts at Vaillant that don't work. Be very careful of their designs. If you want to know a good design, use the Viessmann designs. Anything you can do with Viessmann, you can do with Vaillant, but it'll work if you use the Viessmann design. So
nice. Thanks, Andrew. Yeah. So again, like, I know I do want to say this, like, I'm not promoting Vaillant in over any other brands in this case. Every brand has its merits as well. I'm just showing this because this is, if you do go and work for the Heat Geek umbrella, you'd be primarily installing Vaillant heat pumps. So hence that. But yeah, again, okay. So when I'm talking about lowering the curve and what we call dialing in the curve, where I'm saying keep going lower, this doesn't mean that you have to keep going back to that customer. So, okay, so in real life, like, you're not going to go, okay, I'll come to you every single day and we'll keep turning it down until you get cold and I'll stop. What you could do is obviously remote monitoring and do it remotely, which obviously the easiest way to do this. Obviously let the customer know what you're doing as well, if you want to, which you probably do. You can log in to their system. So left-hand side here, you can change the curve, basically. You can set their minimum flow temperature. So again, minimum flow temperature is important for some customers in the way that they use it as well. You know, it will say, well, I can never go lower than 20 degrees, let's say, or in this case, can't go lower than 15 degrees. So again, it sets that minimum of what you could actually achieve. Again, quite important for some cases, maybe not so important for other cases, but again, you can always change that. The key message I'm sort of trying to push here is this is how you adjust the slope down remotely. Keep doing it. And then obviously the bottom right hand picture there is you monitoring this. And I tried to simplify this. I did have quite another, you know, few pictures on here of showing like refrigerant temperatures and all this kind of stuff, but just to try and simplify everything for the sake of this, you could keep turning the curve down. You could keep watching their internal temperature or the room temperature. Obviously, depending on where that sensoCOMFORT is related in the house, but you know, if we'd set it at 20 degrees, you could keep turning that curve down and you could remotely watch, oh, it didn't hit temperature now, I should probably go up a little bit, rather than waiting for that customer to say, I'm cold. You know, you could probably preempt it a little bit before they notice it. So, you know, as this one starts to tail off here, goes under 20 degrees, it's like, we're probably getting to that stage now where I need to leave it. I need to stop turning it down. So again, obviously, you know, it has more, I don't want to say it only works in winter. It has more effect in winter because obviously you've got a lot more solar gains typically during the, you know, the shoulder months in a way, but there's no reason why you can't do this any time of year technically, obviously as soon as the heating season starts, because you know it's still on that curve. But again, like, to keep dialing it down on the app, keep watching it, or have contact with that customer of, you're probably going to get to a point where you're too cold, which is what we wanted. I'm going to leave you up a little bit, and that's where we're going to stick you. So again, just a little hint and tip if you've never, I think most people already know this, but again, just in case you didn't. Walter, you got a question there, mate?
Yeah, I think I know the answer to Andrew's question. I'll put it in the chat because it's a bit of text. But basically, Vaillant itself says you have multiple zones in a home. Those are rooms, but you can have different circuits in a house. For example, you can have underfloor heating circuit for first and second floor, but also have radiators in those same zones, which will be a different circuit.
Nice.
I think that's the key there, but I will post it in the chat as well.
Perfect, mate. That's great. Thanks a lot for that, mate. I really appreciate that. Thank you. Nice. This bit, I've never taught this successfully, which is probably not a way to introduce this to start off with, but hopefully this is the time. So most, I want to say most, like modern heat pumps, decent heat pumps in a way of putting it, when I was talking about like the low load, so let's say we're getting to, you know, 12 degrees outside or anything like that, and then that heat pump physically can't modulate down any further, we want to stop it from cycling. And you know, I think we all know the effects of cycling on a heat pump, you know, that compressor having to kick start and use more electricity as it starts up and all this kind of stuff. Like, you want to keep it on for as long as possible without turning on and off, basically. But again, in the real world, there's going to be a point where even if the heat pump's been sized perfectly, there's probably a point where it's saying, I can't reduce down anymore. And again, it is an issue, but these modern controllers have a way of overcoming this. And again, as I've sort of led into here, like this energy balance is the way that I've always talked about it. I would use like the energy integral here, as we're going to talk about with the Vaillant, but basically what this is to manage short cycling. Okay, and what it does is basically it tells the compressor when to turn on and when to turn off, and what it's not basing it on is, okay, you've reached temperature, turn off, and now, okay, I've dropped temperature, turn on, because obviously that's no good for efficiency. So this is a way of basically limiting the amount of time that compressor is turning on and off with modern heat pumps. As I say, I have taught this in the past to people, and I feel like sometimes they nod like they get it, and then I'll ask them a question around it and they don't sort of get it. So again, please like raise your hand if you don't understand this at any point. And I've tried to simplify this even further than what I've ever done before, so hopefully people can understand this. You know, we'll see where we get to. So the way, this is not like the scientific way of doing this, is not what Vaillant said, but this is my way of interpreting what this is. Okay, so energy integral equals the previous value plus the actual flow temperature minus the target flow temperature. Okay, and I'm going to break this down, obviously, because that means nothing to anyone at the minute. But basically what I'm saying is energy integral is basically, it's a counter, and it's going to say, okay, how many minutes have you been away from the actual, from the target flow temperature. Okay, so my curve has a target flow temperature all the way across. And what it's going to say is, okay, so what is my target flow temperature? Let's say it was, I don't know, 30 degrees. What's my actual flow temperature at this one moment in time? Well, it's 33 degrees. Okay, so it's going to say, okay, so you're 3 degrees over your target. And then it's going to say, okay, 1 minute later, what are you now? And then all them numbers are going to add up. Okay, so means nothing to anybody. But hopefully this sort of helps. That formula, my own formula, again, yeah, simplified as much as I can, is across the top there. I'm going to start here. So time is 0. So this is the very start of when we're going to start counting this. I've used them examples. Didn't realize that. Target flow temperature, I've used 30 degrees. Actual flow temperature, 33 degrees. Integral score, 0. So at 0 on the Vaillant unit, that is the preset to turn the compressor off. So again, our target was 30 degrees. Our actual flow temperature is 33 degrees. It can't modulate down any further. It turns off. What we don't want it to do is 2 minutes later, just hit back in and turn on. Okay, so how is it going to stop it from doing that? This is what happens. So 1 minute after this, it's going to look at the temperatures again. Okay, and it looks at these temperatures again, and I've used the exact same temperatures to start off with because it's only been going for 1 minute. Okay, so that heat is still going around the system and it's not being able to dissipate at this one point in time, 1 minute later. So our target temperature is still 30 degrees, this one moment in time. Actual flow temperature is still 33 degrees. And because we've been going for 1 minute, what we're going to do is our previous value, we're going to add that 3 degree difference onto that. Is anybody completely lost straight away? Look at the formula. Previous value was 0. Actual flow temperature minus target flow temperature. So you got +3 there. Okay, so your actual target is over that. Add that +3 onto the 0. Your integral score at this one moment in time is +3. I'll tell you what all this means later, but I just want to see that people are getting this step by step. Yeah, nice. Steve?
So going like this, are you suggesting that in another minute the integral score would be 6?
Yes, exactly. Nice, mate. Got it. So yeah, so it's 6. And again, if you're lost, this is the time to shout up because there's like another 3 or 4 slides on this. 2 minutes in now. So first minute, like we had 30 and 33, it's +3. Okay. Next is 1 minute later. So we're now 2 minutes from the very start, but again, it doesn't matter. It's going up in 1 minute. You've still got a 3 degree difference between actual and target. Okay, so we still can't get rid of that heat in this case. So we add the previous value was 3. We add our new difference in temperature, which is 3 together. And then we've got +6 as our score now. Okay, I'm praying. I've just put that same one on there. So that's where we finished up. We finished up on 2 minutes. We had an integral score of +6. Again, it does make sense at the end, hopefully, of what these numbers actually mean. I've now gone to 3 minutes. 3 minutes. What's happened now, and again, forget the integral score for a minute. Let's just look at what the target flow temperature and the actual flow temperature is doing. The compressor turned off at 0. Let me just go back. Sorry, I didn't really emphasize that too much. So compressor turns off. So status at 0 minutes was compressor had turned off at that point. So obviously now there's no heat going into the property. It's still just the heat that's basically still circulating around the system. Okay, so I've said heat pump's still off there, but you know, technically it's compressor. The circulating pump is still going up this whole time. Stevie, you got another question, mate?
Yeah, mate. So it started this here, obviously, on the left-hand side, time 0 minutes. By the time we get to the integral score of 6, has the actual appliance been running for 2 minutes at this point?
So the compressor's not been running. The compressor is off this whole time. The circulation pump is still going, mate. So it's still circulating that water around the system, mate. Yeah, good question.
No.
Which is why this happens now with 3 minutes. So because that heat's still going around that system, then if it can, it's going to get away into the air, basically. It's going to transfer its heat. So the actual flow temperature now has dropped down to 31. Okay, so look at the time 2. It was actual flow temperature was 33. Target flow temperature was 30. Okay, at that one point, it's gone another minute round now, and it's lost 2 degrees. Okay, so now our actual flow temperature is only 31 now. Target flow temperature is still 30. I've used 30 all the way across to keep this nice and easy. Okay, so target flow temperature is 30, actual flow temperature is 31, because it's been 3 minutes now since the compressor turned off, and it's still getting its heat away into the property. The difference in temperature now on number 3, or 3 minutes, is only 1 degree between 30 and 31. So I just add that 1 degree onto my previous score. Okay, so now I'm at +7. Okay, This is so boring, I'm sorry, but I sort of wanted to make sure everyone gets every single stage. Step 4, we're not going to 60 minutes, don't worry. Someone wants to join. This is like the worst time for anyone to join this. I mean, I have no idea what's going on. 4 minutes in, we've lost another degree. Okay, so target is still 30. Actual is now 30 as well. Okay, so now we've got 0. So we don't add 0 onto the previous one. Okay, you can probably see what's going to happen now. I'm not going to go all the way through, as I say. So that was our previous one. So we're at +7. Now, the actual flow temperature drops below the target flow temperature. What we do not want it to do, this is what changes from a good heat pump to a better heat pump in a way. We do not want it to go, okay, I've dropped down now, let's turn back on. Yeah. What we want it to do is see what happens next. We don't want it to be on and off all the time. We want to see like, how long can we get away with this? So again, target flow temperature is still 30. Actual flow temperature is now 29. It's dropping below what the curve is telling it to do. Okay. So now stick with this. It's now minus because it's actual flow temperature minus minus target temperature. So now it's flipped. Okay. Can you see the difference between that? So now we're going to take that number off the previous number. This is where I lose people. Okay. Walter?
Yeah, you're just going back to 1. So you have the energy that you put in a surplus, you just deduct it now, and then you go back to 1, to 0. And then the compressor will turn on, I think.
Sort of. So good question. Good question. Let me go back all the way to the beginning. Really sorry. 0 is when the compressor turns off.
Yes.
Okay. Stick with me and I'll explain it all at the end with that bit. Okay. Just remember that the compressor is off at 0. Yeah. This is for the Vaillant. Okay. We are now, where were we? We're here. Okay. So now we're minusing, as you rightly said. Okay. So now instead of +7, now we're -6 because we've now got a deficit of -1. 5 minutes in. 6 minutes in. I've gone a bit crazy and I've said it's now dropped 3 degrees. Okay, it's dropped an extra 2 degrees on that. Okay, so the difference in temperature now is 3. That's okay. So we've got that 3 degrees in difference minus. So we're going to take that off the previous score, which was 6, and now we're at +3. Okay. Don't worry, I'm not going all the way through. But, so that's where we're at now. 7 minutes, we drop again. Again, I'm going a little bit crazy. I'm saying it's dropping in 2 degree increments now. It wouldn't do this in real life. It'd be a lot slower than this. It'd stay at like 6 minutes, 7 minutes for ages. But again, that'd be the most boring session ever, which this is probably going to turn into. Okay, so now at 7 minutes, we're now actual flow temperature is 25, target flow temperature is 30. Again, what's the difference? Take that off there. We've now dropped into minus figures. Okay, this is the bit now where it's like the heat pump, it's not panicking. It's like, okay, I probably need to start thinking about what's going to happen next. Okay, so the heat pump is still turned off here. It's gone below that 0. 0 is when the heat pump turns off, okay? Oh, the compressor turns off. Again, we're going down again. I've gone down to -3. I'm going to stop it at -3, okay? So we're, hopefully, does everyone understand? Just forget, I'll take it off a minute. So does everyone get that score is, it's being added on each step. It's checking it every single minute. It's like, what's happening now? What's happening now? And then you're getting this score, this integral score. Okay. So that's where we ended up there at 8 minutes. Then I've got bored with explaining it all, and I've said like, okay, etc., until we get to integral score. This is just for the Vaillant. Integral score of -60. Okay. So when it gets to -60, that's like, okay, this has been off for too long now. There's a chance that house is now going to start getting cold. That air temperature is going to get cold. At -60 on the Vaillant as a preset, that's when the compressor says, I should probably turn back on now. Okay, so it's counted down. It's gone from plus figures. And again, that was great because, you know, it's just had extra surplus heat going round, but then it started to slow down. Again, it's gone into minus, which is still fine. Like, you know, it's not going to make too much difference to the air temperature in a lot of houses. It's got to -60. It's gone on for maybe like 20 minutes or whatever. And it's finally said, we're at -60 now. And then that's when it's like, okay, compressor, come back on. Stevie? You're on mute. Sorry, mate.
Yeah, just to confirm, is that factory settings -60? That is when it will turn back on. Is that what you're saying?
Yeah. So
clarifying that. Yeah.
When the Vaillant comes, it's preset at -60.
Okay, got you.
Again, I don't want to. With all of this, what I don't want to do is tell people how to set it up because it has to be set up depending on your system and your customer.
Yeah.
What I would say, and again, take this how you want. Some installers, if they notice cycling, they can go into the settings and you can do this. You can't do it on the sensoCOMFORT, you have to do it on the actual interface unit. You can go into the settings and you can say, okay, change the preset from -60 to -100. And some installers do that, and you can get away with that in some properties. What's an issue with, again, you've only just this is probably the first time people have heard this. So if I went to -100, what's a potential risk there?
House can get too cold.
Nice, mate. It's potentially too long of a swing for some properties and for some customers. So the longer it is, probably the more efficient it's going to be, because probably not more efficient, but less cycling it's going to be. But there's a potential that 20 degrees or 18 degrees could now drop to 15 degrees inside your property. So again, yeah, good point. David, you got your hand up there, mate. You're on mute if you're talking. Sorry, David, I can't see your mouth. Sorry.
Yeah, so on a well-insulated property, you'd most probably get away with dropping it to 100. On something that's a bit higher on the heat loss, you couldn't take it down that far. That's
generally, mate. Generally, in that way of thinking, I'll be completely honest. Like -60 is probably okay for most systems. Like if you actually monitor systems, but there's so much more that comes into this as well. And again, like this is nice to understand this, because it's like, I mean, there's a risk of me saying this. It depends how oversized your heat pump is. Like, and what I've always preached, and what we should all preach, is like, don't put massively oversized heat pumps into properties. This sort of mitigates this, and I take that in the way that you want. But like, if you've got a good control system, cycling probably isn't an issue unless you've massively oversized your heat pump. And take that in the way you want. Like, I'm not telling everyone to go and fit 12 kilowatt heat pumps in 3 kilowatt heat losses, because that's obviously not right. But cycling isn't the biggest issue that people taught 10 years ago, when we didn't have these kind of controls in some heat. That's when it was like, well, it's going to cycle on and off, because obviously it would. When you've got this kind of control system and a clever control system, cycling isn't the issue that it was even just a few years ago on some heat pumps. Stevie, do you have another question then, mate? Sorry,
just to say, it's kind of just a sort of another tool in your arsenal, really, to try and tweak things. If you have got an oversized heat pump, it's something worth thinking about. Right?
100%, mate. 100%. And again, like there's so many reasons why it could be oversized on purpose. And again, it's again, I don't want to use Adam's words, but there's no panacea with this. Like, just base it on what's in front of you and adjust to what's in front of you. Like, like use it as that. So yeah, and I hope people understand that energy balance. And when I was at ERA, that's how it used to work as well. And again, like when I first heard about it, I was like, I have no idea what you're talking about. These Swedish guys are telling me all this stuff, and I was just like, explain it again. And then when you finally get it, it's then really hard to explain to somebody else, because you need something wrote down. Like every time I've tried to explain this, I can't do it off the top of my head. Of okay, take 1 minute, and you need to write this down. If you're trying to explain this to another installer or to an apprentice, please write it down. Have minutes across the top. Have target flow temperature. Have actual flow temperature. In my experience, I can't do it verbally. So yeah, Andrew, you got your hand up there, mate.
I think you explained it very well. I understand it completely. I don't agree with it, but I understand it. I think there's a better way of approaching this. I've been working on a formula recently. If you look at the minimum output of a heat pump in the worst condition, which is when it's approaching the time of year when you don't want to use it, there's going to be an oversupply of energy when the heat pump is on its lowest output. And you can express that as a ratio against the load in the property and the output of the heat pump. And usually it's going to be a far larger output from the heat pump than it is a load on the system. And you can use that ratio to time the cycle time for your heat pump based on the volume of water in the system. So you can actually calculate the ideal volume for what I would like to use, which is the minimum runtime. And I've been checking with the companies. Viessmann have said theirs is a special design because of the internal buffer. It needs a minimum runtime of 2 minutes. Vaillant have said they think theirs is 2 minutes, and Grant have said theirs is definitely 10 minutes. So once you know your minimum runtime, and that runtime's going to be, I've taken a punt at +18 outside, which is kind of the last days you might want your heat pump to run. You can work it out on that ratio, work out your system volume. And if your volume isn't adequate, you can add the additional volume with the volumizer that you need to get that minimum runtime. And that minimum runtime, if you're abiding by that, your cycle time will be far, far greater than the minimum runtime. And for me, the minimum runtime, I think, is the most important thing, because you've got to have time for operation to go on. You don't want the thing. You think about what I've just said. If you followed it, it could come on for 1 minute, but take another 25 minutes before it used up all the stored energy that it's accrued in the 1 minute of running. And that would just give you this blip of function, which is really counterproductive for a heat pump. So you want it to run for a set period of time to minimize wear. And I was guessing this. I was talking to another M&E engineer about it, and we guesstimated somewhere between 10 and 20 minutes. He was sizing a system based on 20. I wanted to go for 10, and we went for 15. But Grant have come back and said 10 for theirs, and the others are saying 2. But either way, once you've got that theory, if you can set that minimum runtime, you've got an idea of what damage you are or you aren't doing to your heat pump during the startup cycle. And you will get a proportion. I just drew the little graph here. I don't know how good it is. I don't know if you can see it.
Not quite, but if you took a picture and send it in, we could.
But the point is that the rate of rise is constant, as is the rate of fall. The rate of fall. They're just different to each other. So as long as you're spending longer with your flow temperature above the hysteresis line, equal to the time spent below, the rise and fall, the effect on energy transfer into the property should be proportional. So you can have a kind of blip up and then a long, steady decline, and you can calculate it through. I don't think it's wrong, but I haven't put it on my YouTube yet, just in case it is. I'm just trying to get information on it, but I quite like that theory. So maybe I'll send it through to you, Lewis, and you can
please do. Again,
see if you can critique it for me.
Yeah, so. No, I'd love to. Thanks, Andrew. I appreciate that.
No problem.
Again, that's what we want. Like new ways of thinking and things that people never spoke about before. It's really nice to hear that. And as Andrew said there, volume has a massive part in this, how this works as well, and what you set this to. You know, if you've got a property and you physically can't add any more volume to it, this is another way of potentially, you know, sorting out that issue of short cycling just by playing about with these settings. Which is why, again, I think it's massively important that people get a heat pump in their own house, because this is the way to, you know, work this out and work out how it actually works in real life, or if you've got a willing customer. And just on the back of that as well, I don't know if anyone knows Mick Wall. He's like one of the, he's not even in the heating industry, but he's just got a Vaillant Aerotherm heat pump. And, you know, some of the blogs he's put about these controls and stuff, like it goes into the nth degrees, Energy Stats UK off the top of my head. And, you know, it explains these kind of things as someone who's really gone into this on his own house and really worked out what this affects. And I'd advise anyone who's working on a Vaillant to look at that and just see, you know, the ins and outs of how these controls actually work without having to play about with it in someone's home. Stevie?
Hi there, could you just say who was that again?
Mick Wall. So it's, I'm sure if anyone knows it, it's Energy Stats with like a hyphen, I think, .uk, his website. And he does loads of blogs and stuff like that. But yeah, he's great, Mick. He's in that book that I wrote, and he's getting them for a heat pump in his home. And, you know, it's like, again, like, yeah, really, really knowledgeable, great.
Oh.
Probably the expert. Yeah.
Perfect. Yes.
It's 6 o'clock there, everyone. So again, apologies. This is going to run over a little bit. Probably that energy balance, as I sort of assumed it would do. Again, the recording will be on Facebook and everything. So if you want to drop off, you know, like, perfectly fine to do so. Hopefully people understood that. If you didn't, watch the recording back, and again, hopefully, you know, it sinks in, or drop me some messages and I'll try even better to, you know, to simplify it. So again, we've looked at what the old system was, you know, like your S plans with your on-off starts and all that kind of stuff. What we want to be doing is going to priority domestic hot water. Again, teaching some people to suck eggs if you've been in this world for long enough. But again, just remember we're back when you weren't, and this was brand new to you. So this is the recap, just for comparison purposes. This is not priority domestic hot water. I just wanted to point that out in case anyone's just joined and was like, oh, this is, yeah. So this is the old way of doing it. This is an S plan. This is priority hot water. Really, really straightforward, simple way of doing it. And this is on a diverter valve that's got a spring return, okay? And what that means is basically when it's got power, it's moved over. When it's lost power, it springs return back to a certain point. Okay, so again, if you're new to heat pumps, the way you'd fit this 3-port valve is the opposite to the way you'd usually fit a 3-port valve in the high temp world. I was going to say boiler world then, not in boiler world, in the high temp world, where, you know, you'd go B to bath if you've ever been taught that before. So, you know, you'd put the diverter to hot water. If you get into low temp, you want to be doing B to radiators. And some people say beta buffer, but don't do that. Yeah, well, do that if you need a buffer, but like, don't start explaining it like that. B to radiators, A to hot water now. Complete opposite of what you'd usually do. A to B is obviously still back to the heat source, which in our case is the heat pump. Okay, so when there's no power, it's resting in heating mode, which again, if you think about it, it normally rests in hot water mode for a standard old school 3-port on a wide plan. Okay, so it's completely opposite now because you've flipped turn the valve around. So again, it's resting in heating. And then if it gets power, which is on the right hand side, the divert valve just basically, again, does what it says, diverts over, sends energy to the cylinder. Okay, simple as that. Loses power, rests in heating. So again, that's how it's actually transferring the energy where it comes from to where it needs to go. Really simple way of doing it, because again, if the boiler or the heat pump fires up, it doesn't need to operate the valve. If it fires up for a heating demand, it's just using weather compensation. Okay, and it's just saying, okay, what flow temperature do you want? There you go. It's not having to open the valve in any way. Okay, so that's how it knows the difference between a hot water demand and a heating demand, which that picture on the top of the S-plan would never know. It would never know what temperature do you need at one point in time. This bottom one, this priority hot water, would actually know. And again, like, I think if you've been on Kimbo's course, he explains this perfectly. And again, I'll probably check that out if you've not. But, priority hot water is actually more focused to heating rather than hot water. It's just in the name. It's more to get weather compensation into your system, because you can't have weather compensation on that top system because, it's just switching on and off and doesn't know what demand it's got. So how would it know what temperature to send to at this one point in time? So that's priority hot water in a nutshell. Again, related to real life. With the, you can fit, I think if you did the pressure loss, can't remember what module it was, when we did pressure loss, we talked about KVS values and all that kind of stuff. You can fit whatever valve you wanted to, as long as you factor in the KVS value and the pressure drop across. I've used the SBA with a 28 mil version as a KVS of 11.3, which is massive if you remember back to that. That's quite a big KVS. So again, hardly any pressure loss, not no pressure, very low pressure loss across it. So that's the SB valve. Again, if you were to wire this in, there's none of this stuff. And what I'm trying to emphasize here is how easy this is actually to do in real life compared to wiring an S-plan. As I say, you've got to think about, oh, that's normally open, and then this goes normally closed, and then all this kind of stuff. Like, this is as simple as black wire goes to AUF, and AUF means open in German, if you're wondering why it's that. So black wire goes to AUF on the board. Blue wire goes to neutral. Brown wire goes to live. You learned that on your first day of your apprenticeship, probably. And it's as simple as that. As it says at the bottom there, green and red typically aren't used. So again, like, it's so much simpler to actually install this as well, rather than, your typical, okay, I need to go, okay, or greys are all permanent live, so I need to do all them together, and then I need to put all this to this. And like, it's just simplifying everything, with also the huge benefit, the efficiency just ramped up. So yeah, that's how you'd wire it into the Aerotherm in this case, or the Aerotherm Plus, sorry. But yeah, again, hopefully that makes sense. Sorry, Andrew, did you get a question there again?
So I don't want to delay you. I don't want to have Heat Geek getting a bill for overtime for you presenting past 6. But you can actually do this as an S plan. You can change the design on the Aerotherm for design 10 instead of design 8. And then you can run 2 motorized valves from the main control panel, and then you can do it as an S plan. But I think the idea is you have to have a bypass in the system if you do it, so that you can't have a failed valve deadheading your pump. But the KVS value on the 2-port valves is higher than the KVS value of the diverter valve. Plus, you get a free 28 mil valve with your cylinder. You've only got to buy one 28 mil zone valve, much cheaper than buying a diverter valve, and just change the design to 10 and wire it in, and you've got a hot water priority system S plan. So it can be done. I've only done it once, but if anyone knows why I shouldn't have done, let me know, and I'll go back and change it.
Great point, Andrew. Love that. Thank you.
No problem.
Beaver, do you have a question, mate?
No, just to Andrew there, was that with the normally open zone valve and the normally closed, or is it 2 normally closed valves? Sorry.
Yeah, if you've got an intelligent controller, it knows it knows its weather comp, it knows its hot water priority, and so it can control whatever valves you want it to do. So if you need to send like a third party on old-fashioned boilers and things like this has mainly come from Kim Betty, this understanding, and Kim Betty's been using Intergas, which are they're really old hat, they're not very advanced. but you can do good things with them. You can kind of make them work if you know all the tricks and all the ins and outs. But if you're fitting something like Vaillant or Viessmann, they already know what they're doing. They're already intelligent. You haven't got to be clever. All you got to do is install by numbers. They'll do all the clever stuff for you. And you can install by numbers an S plan with hot water priority on the Viessmann heat, on the Vaillant heat pump, and on the you don't need to do it on the Viessmann. It's all built inside. There's a few tricks we do with Viessmann to get them to do other bits and pieces, but yeah, so they know their wet. They know that they're hot water priority. They get a signal to the pump or to the boiler that says I need to produce hot water, and they go, okay, close the hot water valve. Close the heating valve and open the hot water valve, or operate a diverter valve, whichever one is being used at the time. So yes, you can do what you can do whatever you want to do with this, but there's always going to be a downside. If you've got a diverter valve, there's always an open channel. So if you're going to have a set of valves that can be closed, then you might want to have a bypass in there, just in case. I don't know if it is a problem to deadhead, but in case it is, if you've got a bypass in there, that won't happen. Okay.
Thanks for that, Andrew. Appreciate that.
No problem.
And then again, like room temp modulation is what we're sort of like now moving on to. I think that a lot of people understand like load compensation, all that kind of stuff, room compensation. Again, if you don't, the training goes through all this kind of stuff. What I sort of wanted to relate this to is the Vaillant controls, because again, as we've sort of found with the language of stuff, it's not obvious what these things mean. So again, if you are new to Vaillant, like, you know, in terms of this, one thing you probably don't want to use, and I never say don't do this, but again, like with this, expanded, try not to use that, because expanded basically turns it into an on-off stat. So again, once you reach your temperature or above your temperature, it's going to turn the heat source off completely. So again, you probably never want to use expanded on a heat pump system, again, unless you've got a really good reason to do that. Inactive is basically, obviously, because we're talking about the room temp modulation, inactive means it just runs on pure weather compensation. Okay, so it doesn't use the altering of the curve and everything like that to meet, what the actual temperature of the room is and all that kind of stuff. Again, read into room comp and stuff, because again, I don't want to keep everyone for 3 hours here, but an active obviously brings that in. My key training point on this, again, from my own real world experience, is make sure you've sorted your weather comp curve out first. Because what I mean by that is, if you put this on initially, you possibly could be overcompensating for not dialing your curve in a way. So it's constantly going, oh, I need to change the temperature of this. And actually it's only changing it because you've not got your curve right in the first place. So again, do that thing first where you keep bringing it down. And then if the customer then says, I'm getting too warm, like overall, or I'm too cold overall, and you're like, well, the curve's right, I can see that it's right. That's when you might need to turn it on active. So what I'm trying to say is, before you go on to active, my advice, I mean, you can do what you want. My advice is to get that curve right on weather comp first, and then you can bring in active, for these properties where, potentially, as it says there, which properties would you use? That's the ones where, you've got high internal gains for whatever reason, so possibly high levels of insulation, where when you do put heat in through cooking or whatever, it's actually hard for it to escape. Or, obviously solar gains, if there's loads of glass, which, a lot of properties do have now. That's when these kind of controls are good. But they're only good as long as you've already dialed your weather compensation in, because they're probably overcompensating for the fact that your weather comp curve is out. So again, a little bit of advice on that. Again, won't go too far into it, because I sort of wanted to get to hot water controls. Again, there's not too much long left now. Sorry about going over again. But again, hopefully people are benefiting from this. So that's heating controls. And again, with the energy balance and all that kind of stuff, that's just for heating. Okay, it's not referring to hot water. So again, this is where we're separating now. This is hot water controls. And again, if I was doing this without being constrained on time, I'd start asking a few questions around, like the effects of volume and all that kind of stuff on the cylinder. But, just to keep this simplified, like, if you're setting your store temperature, what you technically want to do, and I know it sounds like common sense, but you want to set it for basically, the maximum or the minimum you can actually get away with that individual customer. So it's not, I set all my store temps to 50 degrees or I set all my store temps to 45 degrees. It's like, yeah, but that doesn't make any sense, because that customer could just live on their own. They've got a 300 litre cylinder, or that customer could have 5 people in the house with a 150 litre cylinder. So key point on this, work out what the demand is, see what volume they've actually got stored there. And then again, it's an assessment. It's a it's a way of just keep bringing it down until you run out of hot water. It's like, okay, ramp it up a little bit. And again, that's how you find your maximum with that. There's obviously so many more things that come into this, you know, time of use tariffs, all this kind of stuff. So set it up with that individual customer in mind. But I think the key message, and again, I think a lot of people are already aware of this, is that, you know, if you've got a 300 litre cylinder and they're never going to fully drain that 300 litres of cylinder, and they're only going to have a shower at 40 degrees, then, you know, set your store temp just a little bit above 40 degrees. There's no point in heating 300 litres of water to 60 degrees when they're only going to use the top temp of it. So, you know, but again, on the flip side of that, if they've got a small cylinder in terms of the size of like volume compared to the demand, you might need to set a higher store temperature so that more of the cylinder is at usable shower water rather than just the top third of it. So again, it's based on engineering judgment, but also playing about with the controls of what can we actually get away with on this one day. And obviously the most efficient way to run your cylinder in terms of like setting the times up and the temperatures and stuff is to completely drain that as much of that hot water as you can in one go, because then when that coil gets hot, it can transfer its energy a lot quicker to something that's cooler. Okay, so you don't want to be ramping it up every like 10 minutes or something, because it's going to be using a lot of energy. You want to see if you can actually fully drain that cylinder of heat before you actually start to heat it up. But again, in the real world, that's not always practical. So again, like just having the knowledge and then applying it in different situations is the key message here. In terms of flow temperature on the right now, so that was store temperature of like what you actually set the cylinder store to. This is flow temperature of how high you actually set basically the hysteresis between the flow temperature and your store temperature. If you want a rapid reheat time, you know, set your flow temperature, you know, as it says there, possibly at 20 degrees above on your hysteresis. So your flow temperature coming into that cylinder really hot, so you can get that 50 degrees quicker. If you want a slow but more efficient reheat, again, your flow temperatures come down. It's more like closer to what your target temperature is, but obviously it's going to take a bit longer because your flow temperature is less. So again, it's depending on what that customer wants and also the size and the volume of the cylinder. There's no one answer for this. You know, you just got to take this knowledge and apply it. Walter?
What's the thing with the cross through it?
With the what, sorry?
On the screen, there's a symbol with.
Okay, yes.
What is it?
Yeah, it's terrible, that, isn't it? So that's your. Oh, it's all the way back. That's your modern, like your unvented cylinder stat, basically. Yeah, it's a good question. So you know, like your cylinder stat that basically reaches 60 degrees and turns off. Yeah, we're saying don't use that because it's just the same as an on-off stat. Use a sensor. Yeah, so you know the sensor that actually goes back to the heat pump that tells it what temperature it is. But yeah, good question, mate. Yeah, sorry, it wasn't as obvious as what I was expecting there. Sorry. But yeah, same thing. Just to apply that same knowledge that you've already learned for your heating into your hot water systems, and then again they work the exact same way in a way. So yeah. And again, if you want to, again, I'm really sorry. I just want to pass everything on the cam for. Oh, it's the last one. You can reuse, and take this in the right way, you can reuse a standard unvented cylinder on a heat pump system. I think we all have this knowledge that, you know, when you go in and you're like, we're getting a heat pump, so it needs to have a massive coil and stuff. I mean, that would be great, yeah, but you could actually do calculations and work out, could you keep that original one? You just might need to set it at a higher temperature. And again, like, you know, that could save that customer $2,000 on an install if you've done your calculations correctly. You know, the efficiency won't be as great as, you know, obviously a larger coil, which obviously we all know is more efficient. But again, like you could do these calculations and say, oh, actually, you can probably keep that unvented cylinder because, you know, like, again, it's just all based on design, really. And it's the same thing with radiators, you know, it's the exact same thing. If it's a smaller radiator, yeah, you could keep it. Your efficiency is not going to be great. But again, it's that conversation you could have with that customer. But yeah. So, again, I'm trying to cram as much as I can in here, sorry. But a couple of things to note here, like sort of relating to what I was just showing on the previous slide. So the cylinder charging hysteresis, which is this one here. So basically that refers to the temperature drop below the domestic hot water set point that must occur before the system basically starts reheating again. Okay, so that basically stops cycling. So if it drops by like 1 degree, I think people know what hysteresis is anyway, but if you thought like you'd set that to 1, it'd drop by 1 degree, then it basically fire back up again. Okay, so again, for the hysteresis, that's basically how much would it have to drop before it fires back up to get back up to your target temperature. The thing I wanted to point out, because of the language here, is the next one underneath, which is a cylinder charging offset. That's the one where it's the flow temperature of basically what you're sending into the coil. So the two differences there. So that cylinder charging hysteresis, that's your set point in terms of your store temp in a way. The one underneath is your flow temperature. So again, you know, with this kind of stuff, like the lower you can get it, technically the better, but there's a more chance of possibly cycling with that. So, you know, if you've did I put it in that? If you've got the slow efficient reheat sort of thing there, but it's a smaller delta T between the store and the actual flow temp. If your coil's not big enough, you've got a chance of that hitting temperature all the time and not being able to give its heat away. So it's going to potentially cycle more. But again, if you've got a huge coil, you can set that down as low as possible. And to be fair, what we advise, if you've got the Newark Heat Geek cylinder, like a super cylinder, because the coil's that big, we say set that to 0 rather than 5, because the coil's that big that it's never going to it's not going to be able to heat up that much sort of thing. It's always giving its heat away because it's just so big. But again, if you've got a smaller coil, that charge and offset might need to be higher than that. So again, if you don't get that, hopefully you can on the recording, but bigger the coil, basically the lower you want to go with this kind of stuff. Hopefully that makes sense. Again, you've got your maximum charging time there because it's priority hot water, so you might want to think about how often this would be off, compared to that kind of stuff. And again, reheat times are so important with obviously this kind of system that you could have a really efficient reheat time, but again, depending on the size of your heat pump, depending on the volume of your cylinder, that could mean that your heating's off for 3 hours in some cases. So again, you've got to be careful on how you're reheating these cylinders and what time you're reheating these cylinders, more importantly as well. So again, there's so many things to think about in there, but once you get used to this kind of stuff, you'll get into a pattern of usually what you do, and then some occasions where you change it. That's another thing I can talk about. Anti-cycle time, cylinder charge anti-cycle time. So again, if it's done a reheat, how long will it wait before it does a reheat again? If you're installing a mini store or any type of thermal store for this kind of stuff, obviously the Heat Geek mini store is probably the one to go to. You don't want to wait 30 minutes because it's obviously trying to reheat every time it's losing heat. So you want to put that to 0. So again, even if it has just reheated, it wants to reheat again. So again, some occasions, if you're fitting a mini stove, put that to 0. Really quick, I'm really sorry about how long this is. So there's Vaillant and hot water has 3 modes, and I just wanted to sort of show people what that means. In normal mode, that means that the compressor runs at max. So if you've got a hot water demand, the compressor runs at max, which in this case is 120. Okay, and that's revs per minute or revolutions per minute. So it's basically the rotational speed of what the compressor runs at. So it's running flat out, basically full output. If you put it in eco mode, the compressor is capped at 50 for up to the 7 kilowatts, and it's capped at 40 for the 10 and the 12 kilowatts. So basically, as you say, the compressor's not running as hard, but what's the potential issue with that? The compressor's not running as hard. Yes, it's more efficient, but what are you getting? Everyone just wants to go. Steve?
Would you get longer reheat times?
Nice, mate. Spot on. Longer reheat times. So again, if you've got let's say you've got a 5 kilowatt heat pump or a 3.5 kilowatt heat pump, and you want to put it in eco mode, you've got a 300 litre cylinder, be prepared for 4 or 5 hour. If you're in eco, yes, to be really efficient, but again, it's going to take you a long time because that compressor's not working as hard. And it's always that trade-off of what does that customer want at that one moment in time, kind of run it at night when they're not going to be using the heating as much and all this kind of thing. So yeah, eco mode's great, but again, use it in the right situations for the right customer. Balance mode, again, is a combination of the two. So basically what it's going to do is the return temp is equal to or below 45. So basically how it starts, it's going to start in normal mode. So it's going to run at max compressor. As soon as the return temp hits 45, it's then going to basically turn down into eco mode. So it's a balance between the two. So again, it's basically sort of how a boiler would work. If it's, not on weather comp, it's going to throw loads of heat at it. And it's like, oh, okay, I need to basically modulate down now. So yeah, that's how it works. Again, watch the video back if you wanted to properly go into that. And that's it. And I know there's so much information there, and hopefully it was relevant. And I'm conscious that, not everything, well, quite a lot of that wasn't even in the course. That's just more of stuff that I think maybe we could potentially look at in future. And, some people are nodding here. So I'm sort of in these kind of things, I'm trying to grasp where do we go next? What do we add into the training that's not in there? Where do people want to go? So I really appreciate people sitting through that and, getting involved there, because quite a lot of that concept might have been new to a lot of people, depending on where you are in your journey in the heat pump industry. So I hope people have got something, even if it was something simple and something really more complex. Hopefully that's helped people. Any questions before we go? Presenting there. No? So yeah, as I say, the next webinar session, which is like the verification webinar, if you wanted to look at the Heat Geek umbrella, that's on September the 3rd, 5 till 6. There's not another one of these sessions in yet. Again, we're going to probably look at feedback about how we do this, what we look at and stuff like that. So again, I'll probably put some messages in the groups or on email to see what people want. Again, I'm really conscious of time here, so I'm sorry for going over, but just want to say thanks to everyone for joining us all the way through this sessions. Hopefully there'll be more in the future, and again, throw some suggestions out at some point in time of what you wanted to see next, and the frequency of these would be great. So but yeah, thanks a lot for everyone for joining through these sessions, and thanks for your input as well. It's been great. Thank you.
Yeah, thanks, Lewis. It's been amazing. Really, really good.
No worries.
Thanks
No
a lot.
worries.
Yeah,
Thanks a lot, everyone.
unfortunately, I only saw about this a couple of days ago, so I really like this. Thanks.
Nice. No problem at all.
Great format. Cheers, then. Bye.
Cheers. Bye.